Hello again, this is James Camp from Lee College in Baytown, Texas, and this is my commentary on Chapter 7 of Big C++ by K. Horstmann, Pointers and Structures. This is Part 1 on pointers. Our chapter goals are to be able to declare, initialize, and use pointers and understand the relationship between arrays and pointers, and then in a later video we'll talk about strings and character pointers, dynamic memory allocation, and structures. A variable contains a value. This is what we've worked with so far. A pointer specifies where a value is located. In other words, a pointer stores the memory location of a variable. In the following illustration, my pointer, my PTR, is a pointer that points to my number, okay? My num is a regular int type variable like we've used so far in this class. It holds an integer value 42. My num happens to be placed at memory location 1001, though so far in this class we haven't really cared about where C++ is storing all of our variables. My pointer is an int type pointer. That is, the value it holds is not an int, but it's the address or memory location of another int type variable. In this case, it holds the location 1001, which is the location of my num. If we change the value of my pointer to 1002, it will now be pointing to your num instead. So a pointer can be made to point at any other integer type variable, or an int type pointer can point at any other int type variable. In C++ and in C, standard C, pointers are important for several reasons. Pointers allow one variable, the pointer, to be used to retrieve or update values for many variables. For example, current account in a banking program could point to my account now and point to our shared account a minute later and point to my child's account after that. Pointers allow you to share values stored in a common variable. For example, janitor.basewage and frycook.basewage could both point to a common variable called minimum wage. This way, if the minimum wage goes up, both janitors and fry cooks would automatically get the raise. Pointers also allow memory to be allocated dynamically. Okay, that means if you have a variable that you didn't know you needed at compile time, you can just create it on the fly with a pointer. It works even better for arrays where, especially in standard C where there aren't string objects and vector objects, pointers let you use strings, arrays, and buffers that you don't know the size of at compile time. And it's this pointer technology that enables the string object and vector object in C++. Finally, pointers make it easier to work with what we call polymorphic objects. That's something we haven't learned about in this class yet, but we will soon, that multiple objects can be of a common sort of super type, okay? So you might have a shape type of which a subclass is circle and another subclass is square. You may not know whether the object you're trying to create is a circle or a square, so you can use a shape pointer to point to either one of them. Okay, now let's get down to some concrete examples. Harry wants a program to manage bank deposits and withdrawals. He wants to say balance plus equals deposit amount or balance minus equals withdrawal amount. But he doesn't always want the deposits and withdrawals to be from the same account. By using a pointer, it's possible to have balance point to a different account at a different time without needing to modify the basic code that he's already written here. An example, Harry starts with a variable for his account balance, Harry's account. It's currently got 0 funds in it. Harry also has a joint account with his spouse, and he wants to use a pointer to access that account the same way he accesses Harry's account. So he declares a pointer variable named account pointer. And the syntax for this is we put the type name and then an asterisk, or star as it's pronounced by C++ programmers. So we would say double star account pointer. Technically, we would really pronounce that pointer to double account pointer. Every byte in RAM has an address. Okay, we're looking at addresses here from 20266 up to 20348. And these are shown in groups of 8 bytes because that's how big a double is. A double is 8 bytes big. So each double-sized memory box gets its own address number. Harry's account is created by C++ and stuffed into the address 20300. So when we declare double star account pointer and assign to it the address of Harry's account using the ampersand operator, account pointer will now hold that 20300. So account pointer now holds the value 20300, which points handily to where Harry's account is in memory. Now, Harry wants to use his account, but he finds out that the balance is 0. So he's going to change his account pointer to point to his joint account by using the statement account pointer equals ampersand joint account. And we would read that as account pointer equals address of joint account. And that's shown down in the little picture here on this slide, that account pointer initially holds 20300 to point to Harry's account. Then we change it to 20312 to point to joint account. Okay, so that lets our pointers point to things, but it would be fairly useless to have just a variable that just holds a memory location. We don't usually want to read out the memory location of a variable. So the star operator also acts as a dereferencing operator. If we type star account pointer instead of just account pointer, star account pointer will dereference the pointer and actually pull the value that account pointer is pointing to. Okay, so if account pointer is currently pointing to joint account and we know that that has $1,000 in it, then this line cout star account pointer will print the value 1,000. And the line at the bottom of the screen here, star account pointer equals star account pointer minus 100, we'll take 100 out of 1,000, we have 900 left, and assign that to the value account pointer is pointing to, which is of course the joint account. This shows what happens when you type star account pointer equals 1,000. It assigns 1,000 to joint account, which account pointer is pointing to. And if you type balance equals star account pointer, it looks up the value in joint account, the value account pointer is pointing to, and assigns that value to balance, which is just a regular variable, not a pointer. Okay, here are some simple examples of pointer syntax. P might hold the value 20300, a memory address. Star P would return 10, which is, it's pointing to M, which is 10. Ampersand N would get a different memory address. P equals ampersand N means P is now 20304. It's now set up to the address of N. Star P now pulls what p is pointing to, which is n, which is 20. And m equals star p, m gets the value 20. Some common errors are to put m equals p. You would have to say m equals star p. M equals p tries to assign a memory address to an int value, and that doesn't work. Ampersand 10, you can't do that. You have to take the address of a variable, not of a literal. Ampersand p, well, that would give you a pointer to another pointer, which isn't usually all that useful. And p equals ampersand x. Well, x is type double, p is type int star, so those aren't compatible. Those aren't type compatible. When a pointer variable is first defined, it holds a random address. Just like when an int is defined, it holds a random integer. Using that pointer and its random address is an error. So if we type double star account pointer, that variable is now going to point to a random memory location. If we then say star account pointer equals 1000, we're going to try to write the value 1000 to an unknown memory location. Chances are that's going to crash our program because we're going to write over something that shouldn't be written over. If you don't already know where you want your pointer to point to when you create it, okay, if you don't have a variable to point it at right away, you can use the value null pointer, N-U-L-L-P-T-R. If you try to dereference a null pointer, that will still cause your program to terminate, but it will not crash your computer at the same time. Okay, so here is Harry's complete banking program. You see, we start by creating Harry's account and a joint account. We create a double star, a pointer to double account pointer, and we point it at the memory location of Harry's account, the address of Harry's account. Then we say star account pointer equals 1000. That's putting an initial deposit into Harry's account. Star account pointer equals star account pointer minus 100. We're taking $100 out of Harry's account, and then we print the balance, C out star account pointer. Now we take account pointer and point it at joint account instead, and then star account pointer equals star account pointer minus 100. We take $100 out of the joint account, and then we print the balance of the joint account. Okay, here are some practices for you. Declare a pointer. Well, here's the situation. We have tour groups P and Q are sharing a bus with a total capacity. So far, count passengers have boarded the bus. So set up pointers P and Q so that each group can know how many seats are left on the bus. So we're going to start by declaring a pointer variable P and initialize P with the address of count. I'll let you sit on that for a second. All right, if you came up with int star P equals ampersand count, that's correct. Now declare the pointer variable Q and make it point to the same thing as P. Okay, if you came up with int star Q equals P, that's the simplest way to do this. You could have also said int star Q equals ampersand count. Okay, complete this statement to check whether there is space on the bus for another passenger using the pointer P. Here, all you need to do is dereference P because P is pointing to count. So you could say if star P less than capacity, and that's all we need to know. Okay. Pause your video here and try to work out what goes in each of these blanks. All right, the first blank is cout star p, so p points to A, which is 1. So the first blank should hold 1. The second blank is cout star p, but p has now been pointed to B, so the second blank should hold 2. The third blank, we've assigned P to point to A and Q to point to A, and then we've taken dereferenced P, so we're pointing at A, and plus that value. So A is now 16. Then we're couting dereference P plus dereference Q, so A plus A. So 16 plus 16 is 32, which is what should go in that blank. Finally, the last blank you should have put a question mark, because this would be printing the contents of P, not what P is pointing to. So the contents of P are a memory location, which would be a nonsense value as far as any of us human readers were concerned. Okay, which leads to another common error, assigning a value to a pointer with forgetting to put the star in front of the pointer's name. A count pointer equals 1000 literally means you're wanting a count pointer to point to memory address 1000, which might not even belong to your program. So that's not a legal statement. I mean, it's legal in C++, but it's not a recommended thing to do. Okay. Another common error is to define two pointers in a single statement where you type double star P comma Q. The star actually doesn't go with the word double, it goes with the letter P. And so what this does is it says create a pointer called P and then a normal variable called Q. You could use that syntax by saying double star P comma star Q as shown at the bottom of the page. But probably the best way to handle pointers is to just declare each one separately. Double star P semicolon, double star Q semicolon. Okay. You may remember, hopefully you remember, defining reference parameters. Reference parameters are something that C++ has, but standard C does not. So if we wanted to accomplish the same thing in standard C, and we can do it in C++ as well if we feel like it, we would have to use a pointer as a variable, as a parameter. Sorry, we'd have to use a pointer as a parameter to a function. So void withdraw double star balance double amount passes balance as a pointer. And then we can dereference balance and say star balance equals star balance minus amount. But when you call the function, you actually have to pass the reference to the variable, not the variable itself. So you could say withdraw ampersand Harry's checking, comma 1000. If this all seems a little more complicated than reference variables, that's because it is. The C++ reference variable was defined as a way to simplify this process. But the compiler, the C++ compiler, actually converts all of those things to pointers in the background. It just doesn't tell you about it. Okay. The next thing we're going to do is talk about the similarity between array variables in C and C++ and C++ pointers. An array variable in C and C++ is actually a pointer to the starting element. So when we declare int a square bracket 10, we're creating an array of size 10, but the variable a is actually just a pointer to the start of that array. You can capture the address of the first element in the array by just saying double star p equals a. Now, p also points to the very first element of A. You can use the array name A in exactly the same way that you could use the pointer P. So if we're given int a square bracket 10, so create an array of size 10, and int star p equals a, int star p equals a, we've now got 2 pointers to the start of the array. And all of these output statements are equivalent. A square bracket 0, star a, star p, p square bracket 0. So you can see the array and the pointer work exactly the same way syntactically in C++. Pointer arithmetic is the practice of adding integers to pointers to sort of move along a series of memory locations. The only place where this really makes sense is an array, because arrays occupy a continuous block of memory. So pointer arithmetic allows you to move along the array with your pointer. So all of these output statements are also the same. A square bracket 3 is the same as star parens a plus 3. Note that if you don't have the parentheses, you're just adding a value of 3 to whatever a is pointing to. Star parens p plus 3 is the same thing, and p square bracket 3 is the same thing. And we call this ability to use arrays as pointers and pointers as arrays array pointer duality. Okay, the array pointer duality law explains why all C++ arrays start with an index of 0. The pointer a is the same thing as a plus 0, and the same thing as a square bracket 0. So by this logic, the first element in an array has to be addressed as or indexed as 0. To put it another way, the index you're passing inside the square brackets when you refer to an array is how many memory boxes to offset from that starting pointer. Okay, so a square bracket 0 means start where the variable is pointing. A square bracket 1 means offset 1 memory location from there. And a square bracket 3 is the same as a plus 3. It's pointing at 3 memory boxes down from the start. Okay, pointer arithmetic also allows you to use a pointer to point to a particular part of an array. So if I declare int star p equals a plus 3, p now sort of permanently points to the third or the fourth element, the third index of array A. Okay, so it points to a square bracket 3 until we change it. It's not really permanent, but it can, but for as long as we want it to, it points to a at 3. This means you can also use a pointer to walk along an array. So if I declare int star p equals a, p initially points to a at 0. I can then set up a loop where I do something with star p, I add it to a sum, or I print it out, or I multiply it by 10, or whatever I want to do with it. And then I say p plus plus, well, p now points to the next element in the array. So I can just walk along the array one element at a time. I could have also put p plus equals 2, and then I could skip along the array using or modifying every other element in the array. There are all sorts of fun tricks you can do with pointer arithmetic. Okay, here are some examples of pointer arithmetic. The one I want to call your attention to is the second from the bottom, star a plus 3. That's a common syntax mistake. That just takes whatever a points to and adds 3 to that. It's not actually moving to the third element after a. You have to put the parentheses around a plus 3 for that little trick to work. Okay. Remember our function that computes the sum of all values in an array by passing a double array and then int size. Well, in the function header sum double a square brackets int size, the C++ compiler actually reads that as a pointer to a double called a and then an integer. Okay, the C++ compiler considers a to be a pointer, not an array, and that's why you have to specify an array size when you pass an array to a function. C++ will not remember the size of that array because it doesn't consider it an array, it considers it a pointer. We call a trick in a programming language like this where you use a more human-readable format to mean something that's a little bit more complicated. We call that syntactic sugar. Okay, syntax is the way you express ideas in a programming language, and sugar, of course, is something that makes the medicine go down, right? So syntactic sugar makes it more palatable to pass an array. In other words, what we should be writing is double sum double star a int size. But for one thing, we didn't know about pointers until now, and for another thing, it makes a lot more sense to pass an array than to pass a pointer when you're trying to write a function that deals with an array. So that is the syntactic sugar that allows you to pass an array when you're really passing a pointer. As a side note, this also explains the funny syntax that we saw when we used the C++ sort function, where we passed the name of the array and then we passed the name of the array plus the size of the array. What you're really doing is passing a pointer to the start of the array and then a pointer to the end of the array. Okay. Another danger is trying to return a pointer. Okay. Let's say we tried to create an array inside a function that held the first and the last values of an input array. And then we return the result. Well, remember, the array that's created inside the function is a local variable. It's going to disappear as soon as the function exits. So double star would point to nothing at all. It would point to a memory location that was no longer there. Well, the memory location is still there, but it's been reused. It will be reused for the next function call or whatever else. So one way to do this is to pass an array to hold the answer, const double values, int size, double result, and then we can assign values to result, and since it was passed into the function, it still exists when the function exits. An alternative fix is to dynamically allocate the result array using the new keyword, but that gets covered later on in this chapter. Okay, we're almost done. One thing about pointer arithmetic is that it's often possible to confuse your readers and confuse yourself with your fancy, funky pointer math. For example, if you write total equals total plus star p plus plus, what you think you're writing there is dereference p, add the value to total, then plus plus p, so it's pointing to the next item in the array. It's not clear whether that's actually what's going to happen or whether it's going to plus plus star p, the value p is pointing to. Parentheses would make that a lot clearer. But another point is that that's just a totally unnecessary thing to write. It's okay to write total equals total plus star p and then p plus plus on a separate line. And in fact, it's preferable to do that. Your book pleads with you, please do not use such terse programming style, because your job as a programmer is not to impress other programmers with how few lines of code you can use. It's to write code that other programmers can understand and help you maintain. Chances are when you go to work after this class as a programmer, you're not going to be hired to write the shortest program you can possibly write. You're going to be hired to write something that will be a durable program that other people in your organization can understand and help maintain. Okay, last point on this part of the presentation, it is possible to create a constant pointer. Okay, what a constant pointer does is it prevents you from modifying the value that P is pointing to. It makes P effectively a constant. Okay, P may not be a constant, but if you access it through, star P, okay, balance in this case may not be a constant, but star P, the reference to balance, is a constant. So you cannot use P because it's declared as a constant pointer. You cannot use P to change the value, but you can still use P to read the value. You can see out star P, that's fine. Or you can add star P to total balance or something like that. So a constant double star value in a parameter in a function is the same as a const double values array in a pointer. A const array parameter and a const pointer parameter are exactly the same thing. Okay. If your head is spinning right now, that's because it probably should be. Pointers are one of the more difficult parts of C++ to wrap your head around. So I'm going to ask you to take a programming break at this point and work on pointer practice 1, where you're doing a variation on the bank account program from this presentation, and pointer practice 2, where you're using pointer arithmetic to pull some values out of an array. Okay. Thank you, good luck, and see you next time.